The class Q, it's a data structure that enforces the order first in, first out. Often the queue is recognized as a line of items. For this particular implementation, we're going to use the queue using a linked list. I know it's a little bit weird to say the linked list, but in reality, we're using the node. We're going to need our helper called node. You can always create the class node outside of the class queue in case you don't want to create an extra file this way. Remember that the node has a value and also has a next, two constructors where you initialize the value and the next. The queue, however, you only have front and rear. Those are your only two items that you have in your queue by using lists. And if you think about it, they're very similar like linked lists because a linked list has a first and last. We just change the name from front and rear, but in reality, you represent the same data structure. We need to have a constructor that basically initializes the front to the rear to the null. It doesn't hurt to have a method called isEmpty. It basically checks if the front is the null. If that is true, return true, otherwise false. Now we have to use three methods: enqueue, peek, and dequeue. Those are the three methods that are required for a queue. Enqueue is the corresponding adding. If you want to compare with the stack, it will be the push. The only difference is that we're not going to enqueue into the top. We're going to add it to the rear. Peek, it gives you whatever is on the front, and dequeue removes the front. Having said that, we need to understand that the signature of public enqueue is void, and we're going to provide a value x. The value peek returns a string and does not take any parameter. In similar fashion, dequeue. If you think about it, the enqueue is always adding to the rear. You probably remember something like if it happens to be empty, that only means one thing, that the front and the rear is a new node containing the value x. Otherwise, the rear.next is going to be this new node. And the only thing we have to update is the rear.next to that rear. And the only thing that we need to update is that the rear will be the rear.next. So you probably remember enqueue to have it like this. Remember, we're creating nodes with the values inside. By the way, this is the add. This is exactly the add from linked list. We check if it's empty, then the first and the last are the same, which is the node that we just create. But if it's not, last.next will be the node, and you just have to update the last. How about peek? The peek will return whatever is in the front. First in, first out. How about the dequeue? The dequeue is very similar, but instead of just returning, we have to do something. This is something similar to what we did. We need to hold the front that value and return the temp. But meanwhile, we have to do something to the front, which will be front.next. Let's test this method. Here we're going to create a queue list. I'm going to call it queue for queue. We're going to add a couple elements. So this time we're going to use enqueue. We're going to enqueue, again, some alphabet. A, B, and C. If we pick whatever is in the front, we use key.peek, which expect A. Let's say compile and run this program. So we expect A, we got A. What happened if we dequeue? Which value will be removed? We remove the front. What happened if we remove again and again? We expect A, then B, then C. Let's say compile and run this program. What happened if I try to dequeue an extra? Is that at this point, your front is the null. Let's take a look at the queue list. In dequeue, the front is null, and we will try to attempt to access the value from the null. And Java will complain by saying, you know what, this is a null pointer exception. Let's save, compile, and run this program. As we can see, we can have a null pointer exception because it's already empty. We're trying to access something from the null, which is always a bad idea. How do we fix this? Very similar as we did with the stack. We need to check if it's empty. Then we can throw a new queue_empty exception. Specify the queue is empty. We don't have queue_empty exception, but that's no problem. You can always create a class that extends exception with a string as a constructor that calls the superclass with that string. Remember that in the class, if we decide to do this, we always have to do throws that part as part of the header. It's always important to handle that situation in the main by catching the exception and printing them. Let's save, compile, and run this program and see what happened. Now we can handle it. Now we can say the queue is empty by hiding that null pointer exception. The idea of having these classes, this exception creator, is to wrap the original exception generation. If you remember, in terms of the array, we got an array index out of bounds. Not the best idea to tell the hackers that you're using an array. In this case, if we have a null pointer exception, hackers will know that you're using a list. Instead, what we're doing is that we cover these possible exceptions, the real exceptions, by creating these wrappers of exceptions. Let's go back to the code because we're not done. The DQ is very similar as the peak. So what I always recommend is to make sure you have that case every time we check to access the value. We check if it's empty so we can throw that exception. Analogously, we can do same situation with the queue when we get full. But remember, we're using a node base or a linked list when we have infinite capacity. We don't really have to worry to add more than certain capacities because we always have that infinite capacity with nodes. So now that we have all this exception handling, you can go to the tester and add as many as you want, enqueue or dequeue as many as you want, because it will be covered by that boundary. Also peak.